Hello everyone, I hope you are doing well. So in today's video, we are pretty much going to go through the 2024 VCE sample physics paper that just came out today. And so I pretty much wanted to do some solutions for these, basic detailed solutions, explaining how to basically get those multiple choice answers for this video. And hopefully in the future, I'm going to basically do the short answer questions. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics, or chemistry, you can always email me through this email. If you guys want to basically check out this paper, it just came out on the VCAR website. So you guys want to try it out yourselves, please go and have a try at it. So basically, let's go through this paper. This is my first time looking at it, so let's smash it. If there are any mistakes, of course, if there are any mistakes that you see that you think that are mistakes, please just comment them down below. I will try to look at it, and yeah. So let's do this, guys. Question 1. John measures the mass of his suitcase using a luggage scale, as shown below. He holds the suitcase stationary off the ground. The luggage scale indicates 19.4 kilograms. So the net force acting on the scale is closest to what? Aha! This is the hint. Stationary off the ground. This is the keyword here. We know that if it is stationary off the ground, if it's stationary, it means it's not accelerating. And remember, F net equals mass times acceleration. If your acceleration is 0, it means your net force has to be 0. Beautiful, switch one. So the net force acting on the scale is closest to A, 0 newtons, basically. Beautiful. Question 2. A 250-gram toy car performs a loop in the apparatus shown below. The radius of the car's circular path in the loop is 0.2 meters. When the car reaches point B, it is traveling at a speed of 1.4 meters per second. Which of the following best describes the magnitude and the direction of the force exerted basically by the track on the car when the car is at point B at the top of the circular section of the track? Ignore friction and air resistance. All right, let's have a look at the loop here. So basically, I'm going to just do a detailed here. I'm going to detail it here. So basically, imagine that's the loop. And so basically, the car is going to look like this when it's inside the loop. I'm just going to draw, imagine it's this square, basically, rectangle, sorry. Imagine it's this rectangle and the car's basically backwards. So what are the forces acting on it? Well, of course, there's going to be a force of gravity that's going to be towards the center of the mass, so towards the center of the circle, so force of gravity. Of course, we're going to also have a normal reaction force that the rails push on the car, basically. And this is our normal force. And where is our net force? Our net force is going to be towards the center of the circle. Net force. So what I'm going to do basically is I'm going to take down as positive because it's towards the center of the circle. That's where our net force is. So I'm going to make the net force formula basically now. We know that F net is equal to what? So we're going to add these two up. Because they're both going down and we're taking down as positive, we just basically add them up. Force of gravity plus normal reaction force. Now, what are we trying to calculate? It says the magnitude and the direction of the force exerted by the track on the car. So that's our normal reaction force. So we're trying to calculate N basically. All right, let's have a try at this. So F net is basically mv squared over r. Fg is mg plus N. So N is basically mv squared over r minus mg. Beautiful. So putting all our information in there. So what's the mass of the car? It's 0.25 if I'm not mistaken. 25 grams, was it? Yep, 250 grams. 0.25. Velocity that it was traveling at point B is 1.4 squared, all being divided by your radius. And so our radius is 0.2. Beautiful. And minus your mass, 0.25, g, which is 9.8. Beautiful. So putting this in my calculator, that should give me my normal reaction force. So 0.25, 1.4 squared, 0.2 minus 0.25, 9.8. That gives me 0 newtons. Your normal reaction force is 0. So which one looks like? It's A. Beautiful. Done. Question 3. A recent article in The Conversation noted that changing the speed limit from 50 kilometers per hour to 30 kilometers per hour in the local residential streets in suburban Australia would substantially reduce pedestrian injuries and trauma. For example, lower speed limits would reduce the braking distance required for cars to come to a full stop, and thus reducing the number of collisions incident with pedestrians. Alright, a particular car driving at a speed of 50 kilometers per hour has a braking distance of d under a full braking force. Which of the following is the closest to the braking distance for the same car under the same road conditions under a full braking force but at a speed of 30 kilometers per hour? Alright, so how would I do this? Okay, so let's basically draw a diagram and explain this. So what we have is, let's look at basically driving at 50 kilometers per hour. So that's distance, say this is your distance, and basically this is where I'm going to draw a box as the car. Oops, come on. Why is it really struggling to draw me a book? Wow, okay. I don't know what's really... Come on. There it is. Okay, so we actually have a box. Imagine this is our car, and basically it's first traveling at 50 kilometers per hour. All right. And so we know that basically it would start initially with that velocity, u equals 50. Because it's braking, its final velocity is going to be 0 when it's here. So your final velocity must be 0. And so basically we know S, your displacement, is going to be your braking distance, which is d. And what about acceleration? Now, acceleration we don't know, so I'm going to put a question mark there. We're just going to leave it. So what formula, because I want to get something in terms of d. So what I'm going to try to do is, okay, so I'm going to try to calculate, so I'm going to try to calculate distance, d. So we know that v squared, so basically the formula, v squared equals u squared plus 2as, where v squared is 0, u is 50 squared, plus 2as, which is d basically. And so basically if I get d, which is negative 50 squared over 2a, that's going to give me d. What's that going to be equal to basically? Let's have a try. So negative squared over 2. That's going to give me negative 1/250 over a d. Basically, that's my distance in terms of a, our acceleration. Now, what I'm going to do is basically all the same stuff, but now for the 30 kilometer. So basically, copy this whole thing. And now, basically change this up to 30. And of course, our braking distance is going to be different. So we're going to call it S, which is displacement. So using the same formula again, so basically your initial velocity must be therefore 30. Your final velocity is going to be 0. Your acceleration is unknown basically, but your S is going to be basically just S anyway. All right, so we're going to use the same formula. So V squared equals U squared plus 2AS. So V is 0, U is 30 squared plus 2AS, which is negative 30 squared over 2A, and that's going to be our S, which hence is negative 30 squared over 2. Basically, that's going to give me negative 40A, our S. Done. So we've got something in terms of distance, and our S, our new distance, our new braking distance, which is S. So what we want to basically do is so whichever formula is the closest to the braking distance. Now, this is our newest braking distance. So what it's saying is basically we have this braking distance, which is S, is going to be equal to some ratio, which are these 0.6, 0.5. I'm going to call it X, basically. And it's written in terms of D, our distance, which we already have the formula for it. It's this formula here. So, which is D. All right. So putting this all down here, we get what? Oh, what did I do here? What the hell did I do here? That's supposed to be negative 450. All right, so it's going to basically be S is negative 450A is going to be equal to X times your D, which is basically negative 1/250 X over A. Now, these A's get basically cancel out, and those negatives both cancel out. They become positive, so we get 450 is equal to 1/250X. If divide both sides by 1 to 50. X is going to be what? So 450 divided by 1 to 50. That gives me 0.36. So the number is 0.36 that's here. So it says which of the following is closest. So the closest to 0.36 is this one, 0.35, which is B. So choose B as your answer. Beautiful. I mean, it's such a, I don't know, it's a very long kind of way I think I've worked it out, but that's how I would have done it basically. Yeah, wow. Question 4. Let's have a try at this one. So as part of the physics course, Anna, Bianca, Chris, and Danishru investigate the physics of collisions involving cars. On an internet site that describes what happens during a collision, they found the following statement. In an instant, your car goes from driving to impacting the car in front of you or something else. The car slowly abrupts, and at that point of impact, the car structure will bend or break. The crumbling action works to absorb some of that initial collision forces, protecting the passenger compartment. Okay, I'll be honest with you. This question seems the same as the 2019 VCE physics. There's a multiple choice question that is just the same. Is it the same, actually? The students disagree about the use of the word forces in the statement in the bold text above. Which of the following statements made by the students best identifies the physics of how the crumbling action protects the passengers? This is basically the same question as in the 2019. I think it's the last question in the multiple choice question. It is absolutely the same question. I don't know why they kind of repeated that question, but yeah, I mean, let's do it. So, alright, so disagree about forces. Which of the following statements made by the students best identify the physics of how the crumbling action protects the passengers? So let's say what Anna says. To absorb some of the initial collision speed. What? Okay, we're using the word absorb. There's two words you use absorb for. You use it for momentum or use it for energy. For speed, you absorb speed. That is a rubbish false thing you can say. So straight away, that's rubbish. Bianca, to absorb some of the initial collision kinetic energy, protecting the passenger compartment. Yeah, that sounds good. I mean, you can basically absorb kinetic energy, so that's good. Chris, to absorb some of the initial collision momentum, protecting the passenger. Also, that sounds good. C, Danishru says to absorb some of the initial collision forces. Okay, forces, you don't say absorb forces. I mean, you can say absorb forces, but not in terms of these cases here. So we got B, C. Okay, let's see. Okay, read Bianca. To absorb some of the initial collision kinetic energy, protecting the passenger compartment. Now, okay, so your crumbling zone basically is you have one at the back and one in the front. And so basically when you go at high speeds, you basically have a high initial kinetic energy because let's say you're driving 100 kilometers per hour and you crash. So that front of your crumbling zone in front of you, what it's going to do is basically it's going to crumble. What does crumbling do is basically it takes some of that initial kinetic energy, that high initial kinetic energy, and it basically uses it to crumble itself. So it kind of wastes some of that initial kinetic energy, which is great because what does that mean? You basically you have a low velocity when you hit the wall or something. So in terms of kinetic energy, it does make sense that the crumbling zone would actually absorb kinetic energy basically because, yeah, Chris, to absorb some of the initial collision. I mean, that sounds good too, but it's not, compared to kinetic energy, basically. Yeah, how the crumbling basically breaks down. So it gets sent some, you basically absorb some of that initial kinetic energy and basically lowers the speed for a passenger so he can safely survive the collision. So I think B would be the most, in this case, the best. B is sounding the best here. Question 5, the diagram below shows the electrical field lines between two charges of equal magnitude, which will form best describes the two charges. Okay, so let's have a look at this. So you can see that they're both attracting, so they have to be one of them has to be a positive and one has to be a negative. Now, the one that's positive, of course, the arrows come out. So this one has to be a positive. You can see that these arrows are all coming out, whereas this one has to be negative because the arrows are coming in. So beautiful. The charges are both positive, wrong, not negative. The left-hand charge is positive and the right, beautiful. So C looks right. Describes it beautiful. So the left-hand charge is positive and the right-hand side is negative. Question 6. 3 charges, negative Q, 2Q, and negative 2, are placed at the vertices of a triangle as shown below. The charges are at the same distance from each other. Which of the following arrows best describes the direction of the net force on the charge negative Q? So this question here is just the same as the 2019 and I think the 2021 Northern Hemisphere exams. Basically, these questions are very easy. It's such similar questions that come up in most of these papers. So, yeah, we want to basically find the direction of the net force on negative Q. Okay, let's think about it. So think that you're the negative Q right now. Think that you're negative Q, basically. You're negative Q, and guess what? Let's first break it apart. How does negative Q basically react with that positive 2Q first? Now, because we're both positive and negative, they're going to be attracted. So negative Q is basically going to have a force of attraction towards that 2Q. And now let's have a breakdown of what's going to happen with negative Q and that negative 2Q. So because they're both negative, they're going to be repelling. So basically, this is going to be repelling, like that. And so, that's it. We basically get the net force, basically by adding these forces up. So I'm going to basically do that. If I take that there, take that there, you would have basically, nicely, so let me make this longer. Basically, we'll have a horizontal straight line going to the left. Yep, so like that. Beautiful. Yep, a horizontal straight line going to the left. That looks good. Perfect. Yep. Next question, 7. Let's have a try at this. The diagram below shows a coil placed next to a straight wire. When both the coil and the wire carry an electrical current, there is a force exerted on the wire. The direction of the current are shown by the arrows on the diagram. The point X lies on the axis of the coil. Whichever form best describes the direction of the force on the wire at point X. All right, let's have a try at this. Okay, so we can see that there's current in the coil. So what's the direction of the current? So it's going like this, basically. Yep. All right, so it's going like this. Perfect. So it's basically going like this. So using my right hand grip rule, gripping it. So my thumb is going to go on the, so doing it again, it's going to be the North Pole, basically, is on the left side. Meaning that the South Pole has to be on the right side. So we know how basically, how this is going to go, basically. You're going to have a magnetic field that's going to be produced, going to go like this, you remember? Towards the direction of the north and coming towards the south. And so basically, of course, you're going to get some also magnetic field here. Wow, that's not... Why is it really struggling to make me a nice eclipse? Why? I really... Because basically what you get is... You also... Yes, so you also get an eclipse like this, basically. That's going to form as a magnetic field. Like, oops, come on. Something like that. I'm going to duplicate it also here. You'll get something like this, basically. And so, let me draw in red. Actually, let's draw in purple. So you're going to get field lines coming like this. Coming from the North Pole, going towards the South Pole. Beautiful. Done. So that's going like that. That goes like that. So basically you get, okay. All right, done. So that's our magnetic field that's being produced. Now look at the wire at point X. Let's really label this. So we have a force current being basically going up. So we have a current direction going up from the wire. We also have a magnetic field on it that's going from the left towards the left. So using your right hand slap rule, let's determine the force. So basically you use the right hand slap rule. Your thumb is the direction of the current. So it has to be up. Your fingers are going to be the direction of the magnetic field, which is going to go to the left. And your palm is the force. And so from my one, it's coming out the page. So out the page. Out of the page. Beautiful. So D is your answer. Done. Question 8. Which of the following diagrams correctly represents the force acting on a satellite above the Earth's atmosphere in a stable circular orbit around the Earth? This question has been coming up since I think 2003 exams. It's always one of the most easiest questions to do. Remember, when you're dealing with the Earth and stuff, there's always one force that's going to be acting, and it's always the gravitational force, your force of gravity. Now let's have a look at this question. So we have key, force of gravity, thrust force, centripetal force, and normal force, okay? And let's look at which one is the perfect one. So we want a stable circular orbit. Let's have a look at A. Okay, so the force of gravity on A, it looks great, actually. So you can see that it's towards the center, which is great. But we have a thrust force that's, pushing it. Okay, so if you have a thrust force, what does that do? You're basically increasing your velocity. Now, think about it. We know that velocity is the square root of gmr. If you're increasing your velocity, you're decreasing your orbital radius. It's not going to be any more of a stable orbit. It's going to be like a changing orbit. It's not stable anymore, so that's rubbish. If you have a thrust force, basically pushing it, it's not a stable orbit. Next one. What the hell this is? So FC is the centripetal force. No, the centripetal force is it's your net force. It's basically your force of gravity. It's always towards the center of the Earth, so that's already wrong. Why is the centripetal force going that direction? What about C? Okay, we have a force of gravity going there. Is Fn your normal force? Yes, so we have the normal force going. This is rubbish. We know that there is no normal force acting in a satellite when you're on space. So remember, there's only one force, and that is the force of gravity. So D is basically the best here. There's only one force, which is the force of gravity that basically acts towards the Earth center. So yeah, there is no net force. Beautiful. Nice. Question 9. A light globe rated at 15 watts carries a RMS current of 1.5 amps when connected to an AC power source. Which of the following is closest to the peak-to-peak potential difference that would be measured across the light globe? So the potential difference is the voltage. So we want to basically calculate voltage peak-to-peak. So what's the formula basically? Because I don't look at my summary sheet. Where is that? All right, so peak-to-peak voltage. So peak-to-peak voltage is basically 2√2 RMS basically. Yes, voltage RMS. This is my formula. So basically, I'm going to calculate the RMS voltage because I have the RMS current. So we know that P equals VI, where voltage is basically P over current. Now, we know that this is your RMS voltage, of course, because your current's RMS. So your power is 15 watts divided by your RMS current, which is 1.5. You basically get 10 volts RMS. So putting this into this formula to get peak to peak, you get 28 approximately. So D. Done. Beautiful. Question 10. Students build a simple DC electrical motor using a split ring commutator, a coil of wire, 2 magnets, a battery, and 2 brushes as shown in the diagram below. Perfect. Which of the following modifications to the design of the student's DC motor would increase the torque of the DC motor in the starting position shown? So the first one is replacing the split ring commutator with slip rings. I mean, look, this has nothing got to do with torque if you're going to replace with split rings with slip rings. It's only not, basically what's that going to do? It's just basically, it's not going to have continuous rotation anymore, and it's just going to be basically oscillating in that vertical position. So it's quite useless to do that. And it has nothing to do with torque, so it doesn't even increase torque. Removing the brushes from the design. Wrong. If you remove these brushes over here, you're basically removing the contact that the current, this wire has with the coil itself. So if that happens, I mean, there's no more current. So, and there is no more torque, basically. If there's no current, you're just basically decreasing the force, so there's no torque. That's just decreasing your torque every way. Increasing the resistance of the wire of the coil. Okay, let's think about this. So, to increase torque, it's just so force is equal to N current, length, magnetic. So, if you increase any of these, you increase the force and hence increase your torque. Now, if you're increasing your resistance, now we know about Ohm's law, voltage is IR times your current times your resistance. And so your current is voltage over R. All right, which is, okay. If you increase your resistance, you decrease your current. And if you decrease your current, which is here, you're decreasing the force, and hence this decreases your torque. Rubbish. Decreasing the resistance of the wire. Yes, absolutely. Do the opposite. That is the, oops, what did I do? Do the opposite. Because if you decrease the resistance, you increase current, and if you increase current, it increases the force, and hence your torque. Beautiful. Question 11. A square loop of wire is moved through a uniform magnetic field at a constant speed, as shown below. The magnetic field can be assumed to be at 0, position 1, and position 3. Alright, nice. The graph below shows the flux through a loop as a function of position of the leading edge of the loop. So we have the flux, beautiful. Which of the following diagrams best describes the current in the loop measured by the micrometer as the loop passes through the magnetic field? Okay, let's think about it. Now, they're talking about current versus position. So it's not voltage. But you should realize that, okay, wait, isn't voltage just resistance times your current. What this means is basically voltage is proportional to your current. It means their graphs are going to be similar. So all we got to do basically is just graph the EMF position graph, and it's just basically the same as your current. So yeah, let's do that. So having a look at this here, how do we do that? Remember EMF, the formula for EMF is N, don't write N because we're just looking at this. So it's the change in flux over, change in time. Basically, this means the gradient and has a negative basically. I'm not writing N, but yeah, it has that negative. So basically, let's have a look. Let's have a look at the gradient of this first part here, from here to here. So we can see that the gradient is rising. So it's a positive gradient. Now, this means that this is positive, this part here. But remember, you have to multiply by a negative. So negative positive becomes negative. So pretty much what's that going to do? When you look at your graph, it's going to look like this, your EMF. So it's going to look like straight line. It's going to be in the negative, basically. You can see that it's in the negative below the current's going to be below the, like down. It's going to be downwards. And so basically here we can see that it's basically a gradient of, it's a constant gradient basically, which means that there is, your gradient is 0. So it means that there's no flux and hence no current produced. And now let's have a look at here. Now it's decreasing. So your gradient is negative. So your gradient is negative from here. But remember, you also have to multiply by another negative. So negative, negative become a positive gradient. So what he does is it has to go up like this. It's going to go up like this. And basically look like this. Basically, it's going to look like this. Your current or your EMF basically is going to look like this. There it is. So that's how it should look. Let's have a look at our answers. So which of the following diagram best represents the current in a loop measured by the micrometer as the loop passes through the magnetic field? A is your answer. Beautiful. B is wrong. B, you can see that there's no change. They're all basically positive. One has to be positive and one has to be negative, by the way. Don't get confused. Even though this might look like a wrong answer, they're the same. Because you could have a combination of this, or you could have done this, basically. It doesn't matter. So you could have a combination of this also works. Just the opposite, but you can see that they're alternating. Any of these combinations gives you the full marks anyway. Even if you do it in exams, they tell you to write it, any of these combinations still give you the full marks. So basically it's A, and A is the only one that looks like that. C and D look totally out of misery, so not those. So choose A. Beautiful. Let's have a look at question 12. The output of an AC generator is shown below. The following modifications are made to the generator. Its frequency is doubled and the slip rings at its output are replaced with a split ring commutator, which of the following best results in the resulting output. All right, let's think about it. So the frequency is doubled. We know that frequency is what? 1 over your period. So if you double your frequency, you're basically halving your period. You're actually decreasing. And remember, period is how long does it take for a full cycle. You can see this is a full cycle here. Imagine you half the cycle. So there's going to be 2 cycles. So it's going to basically look like, 1, 2. So it's going to have 2 cycles basically. So which ones have 2? You can see that A and C actually have 1 cycle, so not these. Also, one important thing is that we are using, of course it's going to change your amplitude too, because remember, your EMF or your voltage is your N change in flux over change in time. If your period halves, which means your time halves, your EMF doubles. So basically it's going to be, your amplitude of this graph is going to be doubled. So it's going to be 16. Now both of these have 16, B and D. So it could be any combination. But the key here is that the slip rings are replaced with a split ring commutator. And remember what happens then? If you replace them with a split ring commutator, the waves rectify. So basically it will look like this. This part here will rectify. And so the only combination that gives me that is D basically. This shows that there's a replacement. This is still AC basically. Alright, does that look good? Everything looks good on this. Yep. Slip rings are replaced with split. Beautiful. Question 13, have a try. Let's have a try this. The DC output voltage of a photocell, photovoltaics. This is new in the study design. Please learn this. Photovoltaics is new in the study design, and I can guarantee you in your next exam that you guys are going to have, it's going to be in your exam. So make sure you know photovoltaics. I believe the two things they put new is basically like GPS. You need to understand how GPS, has time dilation. Michael Mendelson, relativity theory, photovoltaics, and I think there was other stuff, but there isn't a lot of changes. It was mostly they took a lot of stuff out of the study design. So you guys are lucky. They took refraction, they took dispersion, polarization. They made they made your life quite easy. So you guys should be thankful for that. But yeah, let's smash through this. The DC output voltage of a photovoltaic cell versus time when exposed to a full sunlight is shown in the diagram below. Now remember, photovoltaics, what they do is they take the sunlight energy and they basically produce DC voltage. So that's why it's basically, you can see that it's a direct, just a constant voltage, constant, DC voltage, direct, current. So, all right, the output is connected to an inverter. Inverter. What an inverter pretty much does is it takes DC, DC output, and it basically, DC input, and it basically produces AC AC output, because what our appliances at home are, they all work in AC basically. So it's very useful to have DC kind of DC current or DC voltage, because we really can't use it for a lot of stuff. You can use it for simple stuff, but our home appliances, like everything that we use, is basically in terms of AC. So that's why it's very important to have an inverter, because it inverts basically and makes it all to AC, DC to AC. All right. In a household rooftop photovoltaic system, which of the following graph best represents the output of the inverter? Remember, let me write these down here. So let's say you have this inverter here. Inverter. Your input, so the thing that you put inside of it. Then the output. So your input, output. So we input DC and it outputs AC basically. So that's what an inverter basically does. And so which of the following best represents? So which one looks like basically AC current? Straight away A is wrong. Remember, this is basically direct current. You can see that it's a straight line. B is basically still DC. It's just a rectified graph. That's wrong. C, yes, C absolutely looks right. This looks like an AC. This looks like AC current basically. And what about D? So D is basically, D is negative, but basically it should be also constant, current. So the constant, DC. Beautiful. So, all right. Sorry, my cat's just, come on, kitty. Oh my God. My cat's in my room, so just need to take her off my table. She just sat on my laptop. All right. Question 14. Cyclotron light is produced by electrons traveling at high velocities. The electrons emit light when they are traveling at a constant speed in a curved path in a cyclotron. True. Electrons emit light in a curved path of a cyclotron because what? Beautiful question. So this is kind of theory, but this is what it is basically. I want to explain how a cyclotron basically works. How does it emit light? So that's the key. How does it emit light? I mean, really, why is it struggling? Why do I struggle to draw a base? Okay, so basically what it is, it's basically a big circle. It's very long. And what it is you take electrons or particles like protons and stuff, and you basically direct them at high velocities, close to the speed of light. So velocities are so high. And so what happens is we basically curve them because we have magnetic fields. Remember, if you have a velocity, if you're going at high velocity and you also have a magnetic field, basically it bends. It bends in a circular arc. So basically that's why it bends in a circular arc. And basically, yeah. And what happens is because, and I think a lot of people still forget, remember that there is, the electrons are accelerating. I think that's a lot of people forget. It's a particle accelerator. It accelerates protons and, particles. How? Because people are like, wait, but it's going at constant speed. Because whenever they hear the word constant speed, they realize, F net 0, your acceleration has to be 0. Wrong. You remember, acceleration is if your constant velocity is basically constant. If you have constant velocity, then your acceleration is 0. Here, yes, it has, a constant, speed, but guess what's changing? The direction is changing because of the magnetic field. So if your direction is changing, it means you don't have a constant velocity. You have a changing velocity, meaning that you have acceleration. So this is the key thing. Basically, what emits that electromagnetic radiation, that light, is basically due to acceleration. And so, yeah, let's have a try at this. Electrons emit light in a curved path of a cyclotron because they emit light when they are accelerated. True, absolute true. They emit light when they are accelerated. They emit light when they are moving near a speed of, light. Basically, this is true also. This is absolutely true, but it doesn't really explain it in terms of that, okay, you can travel at high speeds of light, but in basically a straight line, not in curved, like, not curved, which means that you basically, if you're going in a straight line at a constant speed, you basically have no acceleration. So wrong. That really doesn't explain that. They only emit light when they pass through a magnetic field. Not true. I mean, the magnetic field's only basically curves the electrons. It has nothing to do with light. So that's rubbish. D, they only emit light when they transition between shells and atom. Now, look, this is rubbish. It has nothing to do with the cyclotron itself. They're talking about, like, basically electrons, basically emission spectra or absorption spectra, when basically electrons basically go down energy cells and basically emit energy. And that's wrong. Absolutely. It has to be A. Beautiful. Yeah, I mean, I think this was a alright one. So they emit when they accelerate. True. 15. Let's try this one. The diagram below shows a 6-meter string attached to two fixed ends. The string is vibrated and a standing wave is produced on a string. Which of the following wavelengths could not be produced as a standing wave on the string if it were to vibrate it? Okay, true. You cannot have just basically any string length and you think you can create a standing wave. That's false. So let's use a formula, because we're basically we're trying to see which wavelengths will not produce a standing wave. The way you would want to do this is, I'm looking at the formula for fixed end. So I know that wavelength is 2ln, where n is an integer. This value of n has to be, integer means a whole number, like 1, 2, 3, 4, 5. Yeah, not decimals. If it's a decimal, basically no standing wave is going to be produced. So what we want to do is basically solve for n, which is just basically 2l over lambda, and basically just sub all these in, and the one that gives us a decimal means that there's no standing wave. It's not going to create a standing wave. What a beautiful question to play around with. So the first one is 2, what's the length? It was 6 over 12. So that's going to be 1. Again, 1 is an integer. So wrong. Let's try the next one. So where you can, the next one is basically your length. So your length is just basically 12. I'm just going to leave 12 here. Your lambda is 5. Now here is a decimal. 12 over 5 is going to be not a whole number. So it looks like B is your answer. Let's just check the other ones, why they are wrong. If you summon 4, the next one, that's going to be 3. Basically, if you summon 4, that's going to be 3, which is a whole number. So that produces a standing wave. That's wrong. And what about 3? Also, that's going to be 4. It's going to be an integer value. So not, it's going to create a standing wave. So that's also wrong. So just basically choose B as your answer. Beautiful. Question 16. The spectrum of photons emitted by excited atoms is being investigated by 2 physics students. The atomic energy level of a diagram of an atom being studied in is shown below. Although most of the atoms are in the ground state, some atoms are known to be in excited states to the n equals 2 and n equals 3 excited states. The ionization energy for this atom is 6.2. The lowest energy photon that could be emitted from the excited state atoms is what? So we want the lowest energy. Okay, let's have a look. So we can have a combination of energies that go from n equals 3 to the ground state. But you can see this is a large energy because of the length of the... You also have a... Also, you could be going like this, and also you have a combination going like this. Now, we want the lowest energy photon, basically meaning that which one has the lowest energy. Basically, the one that has the lowest is basically this one over here. Which is what? So 5.2 minus 3.4. Because it has the smallest length, meaning that it has the smallest energy. That's going to be given. So 5.2 minus 3.4, 1.8. Choose B as your answer. Beautiful. What a beautiful last question. Question 17. The Global Positioning System, GPS, makes use of satellites in orbit around the Earth. The student shown in the diagram below is standing on the ground while a GPS satellite passes directly overhead. The Lorentz factor of the GPS satellite is this. Whoa. Now, I think a lot of students get confused. What's this? Basically, what it is, it means your Lorentz factor is 1 plus a very, very small number. Basically, this is what it looks. Your Lorentz factor is going to be like 0.0000000. It's so small, 0, like 5. Now, you're probably like, well, if the Lorentz factor is basically just 1 itself, it looks like it's just 1, just because of this little extra 5. it's kind of negligible. We think it's negligible. Why would we have to like write that extra? Now, okay, GPS, this is why we do take very important precautions. GPS are very precise in terms of measurement. So we need to make sure even those negligible little time those times, we still take them into account. So that's why it's very important for GPS systems to have something like this. So yeah, we have to have it like that, basically. We need to even take that little extra, basically gamma, your Lorentz factor. Even though it's so small, we still take that decimal places. All right, assume that the GPS satellite is traveling along a horizontal path and ignore the effects of the Earth's gravitational field. Assume that both the GPS satellite and the students are in an inertial frame of reference. Beautiful. If exactly 1 second passes as measured on the GPS satellite, how much time elapses for the student? All right, now we should already know that the student is going to basically measure time that's been dilated, and the satellite itself is going to be measuring the proper time. So if exactly 1 second passes as measured from the GPS satellite, so basically when GPS measures time, your T0, your proper time is 1 second. Basically, that's what's happening. It exactly measures 1 second. How much time elapses for the student? So basically, what's the time that's been measured with the student? So your dilated time, basically. So which is basically, you remember dilated time is just your proper time times your gamma, your Lorentz factor, which is basically 1 times this big number, this whole thing here. So, oops. 1 plus 5 times 10 to the negative 11. Beautiful. All right. I mean, that's what they're looking. Okay, so which one looks like that? Looks like C is your answer in that one. Yep. 1. Yep, so 1 is 1 times 1 plus 5 times. Yep, that looks good. Perfect. Question 18. Classical physics predicts that an electron traveling at 2 point blah, blah, blah should have a kinetic energy of this. Oh, this is rubbish, because if you're traveling close to the speed of light, you don't have classical physics. Classical physics is always wrong in terms when you go to the speed of light. However, experiments with electrons traveling at this speed show that their kinetic energy is actually greater. This difference in kinetic energy is due to relativistic effects. Given that the Lorentz factor, gamma of the electrons at this speed is 3.2, which of the following gives the relativistic kinetic energy of an electron traveling at this speed? What a beautiful, easy question. So we know from your formula sheet that EK, your kinetic energy relativistic, is your gamma minus 1 mc squared. So what does that mean? What's your gamma? Our gamma is 3.2 minus 1. Your mass of an electron is 9.1 times 10 to the negative 31 times the speed of light. Beautiful. Squared. So that's going to give me 3.2 minus 1. 9.1 times 10 to the negative 31. 3.0 times 10 to the power of 8. Squared. That gives me basically 1.8 times 10 to the negative 13. Looks like B is your answer in this case. Beautiful. That looks good. Yep. Times 10 to the negative 13 joules. Done. Question 19. As part of an experimental investigation, physics students use a pendulum, as shown below, to indirectly measure the magnitude of the Earth's gravitational field at their location. The students use a constant mass and a constant amplitude of swing, changing only the length of the pendulum and then measuring the time for 5 oscillations. They obtain 4 different time readings for 4 different lengths of the pendulum, whichever form best explains why the student measured the time for 5 oscillations rather than the time for 1 oscillation. Basically, this question is just the same as one of those old questions. I don't remember which exam, but it's basically just similar. It's basically the same as I remember doing this question. So, okay. What it's meaning is like, why do we take 5 oscillations and rather 1? And that's because we want to decrease uncertainty. We want to decrease random error. That's the reason. But so 1 oscillation is quick to see? Not true. That's not the main important thing that we're trying. 5 oscillation to reduce the effect. Nothing to do with air resistance. What's happening? 5 oscillations to reduce the uncertainty of the measured period. Absolutely. So if you're measuring period, remember, what you're trying to do is, why do we repeat an experiment, or like, for example, this 5 oscillations, why we do that is because we want to decrease the uncertainty in what we're measuring, which is our dependent variable. In this question, it's telling us that the dependent variable is the time, your period. So absolutely, you're measuring uncertainty in that. Looks good. 5, auto selection reduces the uncertainty of the measured length. That's not true because that's our independent variable. Our independent variable is the thing that we can manipulate, so not that. Beautiful. Last question, 20. 4 dart players A, B, and C, and D played a modified game of darts. The aim was to hit the bullseye at the center of the dartboard. Each player threw 3 darts. The results of the throws are shown below. All right. Beautiful. Which of the players produced a set of attempts that could be described as precise but inaccurate? Okay, let's think about it. Precision. What is precise? If we want them to be precise, it means that their range of values, how closely are they? Basically, if you have a high precision, it means that your values are very closely related to each other. Accuracy is pretty much how close is the value close to the true value. So in this case, if we want it to be inaccurate, it means, remember, accurate means that it hits the bullseye perfectly. That's what accurate is, because it hits the true value. But if we want accurate, which ones basically don't hit the bullseye? So basically, this one looks like it hits the bullseye. A is wrong. Looks like it's hitting the bullseye. So, all right. B, okay, and yeah, basically the other ones don't hit the bullseye. Now, what we were talking about, we want high precision. Precision means that the values are very closely related to each other. So you can see about player B, basically these values are just random. They're not being hit, so it's not very precise. C, again, random, just being hit everywhere, basically. D is correct. You can see that they actually are all closely related to each other. So his basically results are precise but not accurate because he doesn't hit the bullseye. So it's basically player D. And all right, and that is it. I hopefully should aim to finish the section B in some time later. I hope you guys enjoyed this video and learned something. Please make sure to like and subscribe for more future videos. And yeah, I hope you have a great day and make sure you take care of yourselves. Bye-bye.